Hello and welcome to podcast.init, the podcast about Python and the people who make it great. We're recording today on June 29th, 2015, and your hosts as usual are Tobias, Macey, and Patti. You can follow us on iTunes, Stitcher, or TuneIn Radio, and please give us feedback. You can leave a review on iTunes, contact us on Twitter, send an email to us at hosts@podcastinit.com, or leave a comment on our show notes. And if you'd like, you can support the show by a donation, with details on our site at podcastinit.com. Today we're talking to Damien George, the creator of the MicroPython project. Damien, could you please introduce yourself?
Yeah, hi, thanks for having me on your show. I'm a physicist by profession, but I did in my undergraduate I studied computer engineering and physics and math, so I did a lot of software programming, operating systems level stuff, but also hardware-based things, like working with microcontrollers, and so I got a computer engineering degree, which is sort of like a robotics degree, and that was at the University of Melbourne in Australia, and I also did a PhD in theoretical physics, so that's actually what I do at the moment. I study theoretical physics, and do research as a postdoc into theoretical physics. Right now I'm at the University of Cambridge, and yeah, it's really great. I like thinking about the world and how the world works. But I also like to get my hands dirty and do a lot of programming and working with hardware and things like that.
So MicroPython is just a side project for you?
Yeah, it started out as a side project, but it's grown into something quite large. I've always liked to write programming languages. I think a lot of people who get into computer science, when they discover programming languages and actually making them, it's something that really captures people's imagination and people can get really passionate about the kind of language they like or that they use. Yeah, I don't know. It just gives you power when you actually can make your own language, and you can write it in just the way you want. It was always a hobby of mine to write languages, and I never really had a big one. They were all just hobby ones. But with MicroPython, it was sort of rewriting this existing Python. So technically, it was something that I really enjoyed doing. And yeah, just as a sort of hobby or a side project to start with, just to see if it was even possible to get Python, which is such a dynamic language, to get it to fit on a microcontroller, which is very, very constrained in terms of RAM.
I bet. So as a perfect follow-on to that, how did you get introduced to Python initially?
I guess it was during university when we learnt lots of languages back then. Like we did our introductory course was in Haskell. We also learnt C and Java and C++, and Python was there as well. Just as you're encouraged to learn as many things as you can. We used Unix, so we learnt shell programming. So I guess I didn't actually do a course in Python, but it was just one of those things you pick up, and you gradually get to learn the language as you use it in your studies and then in your hacking as well.
So is there a particular aspect of Python that made you decide to use that over some of the other languages that you learned in your courses, or do you use it more prevalently than any of those other languages?
I really like C. I don't know why. I think because it's low level and you get full access to the hardware, and I like that. So I actually use C a lot. I use C++ a bit, but then Python is my choice of language when it comes to just banging out something quick. Or even, relatively large size, and when you just want to express your thoughts in a much cleaner way, and you're not worried about performance, then I'll choose Python for that.
So is there a particular problem that you were trying to solve when you first had the idea to create the MicroPython board and interpreter?
It was more of a technical challenge, or I like programming, I like languages, and I thought, well, microcontrollers, I have a lot of them lying around, and I've used them for quite a long time. And they, these days, are very sophisticated, the microcontrollers you can buy. And that means they're difficult to fully utilize. And especially if you have to write in C, with a really tiny microcontroller from many years ago, you only had 100 bytes of RAM and you only have a few instructions, and it's quite simple to use. But nowadays, it's a full-on ARM processor, and you've got all these peripherals like I2C and SPI and UART buses and DACs and ADCs and PWM and timers. And to use all of these peripherals requires a lot of programming, and to get the interrupts right and to get all of the low-level things correct on a microcontroller is actually very difficult. And sometimes you just want to, get a microcontroller and make some light flash in response to some button press or maybe some wireless event. And you don't need or you don't want to spend ages and ages hacking at the low level. You just, just like when you're on your PC and you just want to write a quick script to do something, you use Python. So you have a microcontroller and you want to quickly just do something with some motors and sensors or something you have lying around. And I thought, it would be good to have a language like Python to use on the microcontroller. And I mean, the reason that I chose Python for this job was because for one, it's a great language and it's very popular. And so if you already know Python, then going to MicroPython, you already know half of the story. The only other thing you have to learn is sort of a bit how the hardware works. And from the other side, someone who knows a lot about hardware but doesn't know Python, it's easy to pick Python up and then they can control all the stuff they already know. And Python also has lots of really nice features for programming on a microcontroller, which you might not sort of realize that bitwise operations like AND and OR and XOR are there in Python as native operators. And that's what you use all the time on a microcontroller. Python has a good separation between integers and floating points, which is important on a microcontroller. And, it's procedural, which is a good connection with when you're actually making something. You do A, then B, then C, and events happen. So a procedural language is good, but also with classes and object-oriented, you can encapsulate, like, a servo motor with a class, and then you have methods on that servo to make it move. So I thought Python's actually, it allows you to abstract very well the hardware, and it gives you good control, and it's very expressive. So, yeah, it was sort of a no-brainer, really. It was something that, it just fit really well. And then the challenge, of course, was to see if it would actually fit when I wrote the language. So that was the fun bit.
And so are there certain aspects of the MicroPython runtime that make it even easier to deal with some of the hardware concepts that might otherwise be more difficult to grasp, like dealing with interrupts or figuring out which pins to interface with for a given output?
Yeah, so for example with interrupts, you can just register a function to be called when the interrupt occurs. So you can say, okay, when this timer expires, I want you to call this function. And that function can be like a lambda, an anonymous function, or it can be a class method, or just a normal function. So you can get the callback. When you have an interrupt, for example, it's just an event that gets fired by some external event, that is. So for example, if a pin goes high from low or because a switch has been pressed, then an interrupt will fire inside the microcontroller, and you can ask MicroPython to call your function when that interrupt occurs.
So in the video, you mentioned that MicroPython is a complete reimplementation of Python optimized to run on a microcontroller. How hard was it to create an alternative Python implementation? Did you have hard decisions to make as to what to include given the limitations of the hardware?
Well, to start with, I just wanted to see if it was even possible. That meant writing the lexical analyzer to tokenize the input stream from the script, a parser to turn that into a parse tree, and then a compiler to turn it into bytecode, and then the virtual machine, and then the runtime. So all these things, I mean, there could have been some hurdle where it just wasn't going to work for some reason. So I just, to start with, just needed to have proof of concept that I could actually get a REPL up and running, a prompt on the board. And that was the first goal, and I didn't really, everything else was secondary to that. Well, whether or not I had Unicode, or whether or not I had, certain methods on dictionaries or strings, that didn't really matter at that point until I could prove that the REPL would work. So it was, I had to go through lots of tricks to get things to fit in RAM, stuffing integers into pointers and things like that, and interning strings at appropriate moments, trying to use as least RAM as possible. So the way the compiler works is once the parse tree is created, it runs over that parse tree 4 different times, and each time it collects sort of information. So the first pass, it collects information about the symbols, and then about the stack size, and then sort of does some more manipulation, and at the very end, once it knows everything, it can then emit the bytecode. So it tries to be very efficient in RAM in that case, and not to create unnecessary data structures. Just use the one parse tree. And then the bytecode is sort of a compressed version of Python's bytecode. To make sure that it doesn't use much RAM, there's lots and lots and lots of things are stored in read-only memory, like on the flash and not on the RAM. So all the inbuilt modules like the Systom OS and modules like that, they're all pre-compiled and sort of ready to run from read-only memory. So when you import sys, it doesn't take up any RAM because it's already there, and you can run all of the sys functions. So all these things are done, all these tricks are taken in order to minimize the RAM usage. And actually, as a consequence, it makes it efficient as well, because when you import something, there's nothing to do. It just says that, okay, I've imported this module, but it's already been initialized. So it runs relatively efficiently. And that was another thing. A microcontroller is not as powerful as a PC, so you can't just hold lots of resources to compute things. So it's a very fine trade-off between making it run efficiently, making it run without RAM, and also making it run without using up too much code space. So you're really constrained from lots and lots of different directions. And a lot of the time when you're designing parts of the code, you have to make a trade-off. So I could make it run faster and more efficiently, but I might need to use more code space. Or I could use less RAM, but I might need more code space to do the compression. Or I could use more RAM and have less code space. So there's always a trade-off between one of these three things: efficiency, code space, and RAM usage. And it's a pretty fine-tuned system in order to run efficiently and with minimal resource.
I bet. What is the total runtime size of MicroPython, when you sort of first fire it up?
So if you ask about the RAM usage, so you can get a REPL prompt in about 1 kilobyte of RAM. You can type sort of 1 plus 1 in about 2 kilobytes, and it will be able to compute that. So that's parsing, compiling to bytecode, and executing. And most of that RAM is used actually to create the parse tree, because if you type 1 plus 1, there's a bit to do. That also actually includes a little bit of history in your REPL. You've even got tab completion. So there's a lot just in 1 or 2 kilobytes. Yeah, but then if you go beyond that, if you want to write a script that's, 20 lines, you're going to need a few, maybe 5, 10 kilobytes to actually compile that and then have a chance to run it. But still, 5 or 10 kilobytes is very, very small compared to, CPython takes megabytes just to start up and load all of its internals. So yeah, it's pretty minimized. The hardware that we use, so the MicroPython PyBoard, it has 128K RAM, which is used for the stack as well as the heap and the data and VSS segments. But in 128K total RAM for everything, you get an awful lot of room to play. You can create byte arrays that are 20K long without a problem. You can make lists that have 10,000 elements in them. So you've got a lot of room to play. There are other boards that it can run on that have less RAM, that have only say 32K of RAM. A lot of effort being gone into minimizing the RAM, and every time there's an extra addition, it's really got to be checked that it doesn't use more RAM or it doesn't use more stack, or if it does, is it really worth it? So it's not just a project that you can, add stuff to because you want it. You've got to be like, okay, is this feature really going to stay within the micro spirit? Is this feature, unnecessary, or is it really necessary? So we do have to cut back occasionally, and it's not 100% Python because you can't have your cake and eat it, right? You can't have 100% Python running on a microcontroller. But what we try and do is say, okay, let's try and fit 90% of Python, of the most useful parts, into MicroPython, so it's still really as faithful as possible to Python, and it just feels like normal Python when you use it. Maybe there are some edge cases where things don't work exactly as they do in Python, or there's some missing features that are not there because they're hardly ever used. But we try and keep that to a minimum and try and make it work as well as possible. So you can get a script and run it on Python or on MicroPython and it should work the same. And if it doesn't, then we try and fix that so it does. So it's important that it really does follow the C Python specification.
So were there certain pieces of the standard library that you had to leave out because they weren't relevant or took up too much space to run on the MicroPython board?
Yeah, well, there's lots of stuff that doesn't run on there because it's too big or because it doesn't make sense to run on there. Like, I mean, you don't have you don't need argparse. Yeah, and if you don't have any internet connection, you don't have any use for the internet library. So a portion of the C Python standard library is ported to run on MicroPython. Some of it just runs directly. You just take the C Python code and it works. Other parts, there's some built-in modules that you need features for, so they don't work directly. Things like NumPy, for example, that's not going to work because that's written in C specifically for C Python. So we would have to re-implement NumPy if we wanted that to work.
Yeah, there are also big parts of it that are written in Fortran as well, and I imagine that you probably don't want to try and get into the business of writing a Fortran interpreter as well.
Yeah, there's a lot of extra stuff you have to make NumPy work. There's a lot of work you have to do. But yeah, I mean, if something's written in pure Python, which relies only on modules that are sort of working, then it should just work.
So that leads us into our next question. So I know that people who have developed alternative Ruby implementations have run into issues due to the lack of a formal specification for that language. And has the fact that there is a specification for Python made your job easier?
Yeah, definitely. I think Python is very well defined and it's a very robust language when you use it, even though it's a high-level scripting language. It is very robust in the sense that the operations like, integer division or truncation of floats to integers, they're very well specified to, always have this particular behavior. Or for example, the modulus operation, where you take the remainder of a division. In C that has a certain specification, but in Python it's slightly different and it's made slightly different so it's easier to use. But it's very, very well specified. And that's very good because then you read the docs for C Python and, I shouldn't call it C Python, you read the Python docs and you implement as the docs say, and then it works and it matches C Python, which is really good. So, for the most part, all I have to do is just, when I wanted to implement some nitty-gritty feature, just read the Python docs and just follow what they say. And most of the time, you can get by just by doing that, and you don't have to go into the C Python source code to see exactly what they meant. You can sort of just forget about the source code and just write it from the specs. Also, you make lots of tests, and you run those tests against C Python and against MicroPython, and you make sure they match up. That's another way that keeps our code running smoothly, and we don't get hopefully any regression. But it was very good with Python's documentation to have such a formally specified language, and I think that's due part to the fact that it's got multiple implementations like IronPython. So those things lead it to have a very good formal specification.
That's true. I mean, when you think about it, Python already has had a number of implementations for quite a number of years. IronPython and PyPy and Stackless and Jython and all those guys. So that's a really good point. The Ruby multiple implementations, although they've been running for a few years now, aren't nearly as mature. So that has to help. Other people have already perhaps smoothed out some of the rough edges for you.
Yeah. Well, we still find a few rough edges, but they're not common.
The YPy chip seems like an interesting device. What are some ways in which it can be put to use? A MicroPython cluster, for instance?
Yes, that would be one thing you could do. So the YPy is a MicroPython software is a re-implementation of Python, as we've been discussing. The PyBoard is a piece of hardware that runs MicroPython and has all these peripherals like ADC and DAC ports and so on. But MicroPython can run on lots of other hardware. It can run on the PC, or it can run on these other development boards. And the YPy is one that was specifically made to run MicroPython, and it's one chip that is a Wi-Fi transceiver chip, so it connects over Wi-Fi to other Wi-Fi devices, your router or something. And it has a little application processor on this chip which can run MicroPython. And the aim with the Wi-Fi was to have this small, cheap, low power, sort of little wireless chip that runs Python, so you can telnet into it, and you have a Python REPL right there, remotely. So you can plug a battery in, throw it out in the garden, telnet in, and then read the temperature or turn your sprinkler on. Or you can, throw it behind the couch and you've got, turn some lights on from your remote, from your PC or from your phone even, if you want to telnet in from your phone. So it's a really cool sort of remote Python prompt if you give it like that, and you can put it into whatever you like, and you can control whatever you like in your fridge. You send an email to you when the fridge is open, or a tweet. So there's lots of different things you can do. And this is just sort of the touching the surface. And this is all about the Internet of Things, where everything one day will be connected to the Internet, even if it seems crazy right now. It's maybe in the future it's not going to be so crazy to have everything connected and everything having an IP address and stuff. So hopefully, with the Internet of Things, so you can have MicroPython running the Internet of Things, just like normal Python runs the normal Internet.
Indeed. I mean, I guess one of the things that I had kind of envisioned when I read about this and heard about this is some of the robotics projects that you see where they have little swarms of robots that can communicate with each other. And I thought how cool it would be, in addition to being able to sort of have a visual or infrared or whatever other sensor sense of each other, if they could all chat over Wi-Fi and do interesting things and have interesting behaviors as a result.
Yeah, no, definitely. I mean, robotics, it's all connected. It's all hardware and microcontrollers, and you need a control board, some actuators, some motors, some servo motors, and then you just need to connect them all together. So if you have Wi-Fi, that's the solution. Yeah, and you can have a swarm of things, have a Wi-Fi router that they all talk to, and they all communicate with each other, sending some JSON strings, JSON data to each other, telling them where they are, what to do. Yeah, really straightforward to do. I mean, it seems a few years ago making such a thing would be very hard from the hardware and the software point of view. But today, and this has come about just very recently, all these really easy to use Wi-Fi chips, and you just give a power supply, connect them up to some motors. You don't need much hardware knowledge to do that. And then software knowledge, you just write in Python and you've got your little cluster of robots that can run around. So it's pretty exciting times, and I think it's only going to get better with better hardware and more easy to program.
Yeah, it definitely sounds like it would have some pretty interesting applications in the smart home space as well, being able to have multiple sensors networked via the PyBoards or the Wi-Fi modules to be able to transmit information about your entire habitat to different regions within it. So maybe saying, track your progress through the house and, maybe adjust the temperature or start the oven warming as you come downstairs for breakfast, things like that.
I think the cool thing is that it's not just restricted to what someone is selling you. You can program it yourself to do whatever you like, right? So the power is in your hands to program your Python board to behave how you like it. And if you come up with some idea of how you want to automate your house, then you can implement it. I think that's pretty cool.
Are you familiar with the electric imp module? Is that something that the MicroPython implementation would be able to run on, or is the CPU architecture too different from what MicroPython was designed for?
MicroPython can run on many different architectures. It doesn't have to be ARM. It runs on already 3 or 4 different architectures. And I don't remember what the electric imp is. Could be an ARM, but whatever it is, it could probably run on it. The main question is how much RAM does it have? It needs to have about 32k RAM to do interesting things with scripts. So that would be, if it had enough RAM, which probably it does now with the latest revisions of it, then yeah, MicroPython could run on it. There's always scope for someone to port MicroPython to run on some new chip or some new board. And by all means, if anyone is interested in doing that, then please go ahead And once you have it done, you can submit a pull request and we'll see if it's something we can incorporate into the main repository, or at the very least you can just link on the forum and other people can use your code. So we're always looking for people to help contribute, because it's a completely open source project, MIT license, which means you can use the code to do whatever you like. So it's a true open source project, and it's driven by the community now.
So what changes did you have to make to get the Python interpreter to run without an underlying operating system?
So no underlying operating system means that you need to write all of the sort of standard things that you're familiar with yourself. So, for example, memcopy and printf and malloc, all these things need to be implemented. You also need to have sort of some IOs and input and output. So you need to have a USB driver, and you need to be able to send characters in and out of that USB to your PC. You need to write a file system. You need to. So there's lots of those things, and I mean, actually, for me, it's fun. I enjoy doing all that. It's really technically interesting. But yeah, you literally have nothing to start with. You have some RAM, and you have a CPU, and then you've got some peripherals, and in order to control those peripherals, you just got to write bytes to the right addresses in RAM, and you just got to work out what bytes to write where, and then things happen. But luckily, there's drivers for these chips, so it's not as daunting as it sounds. But still, there's a lot of work to do to make it into essentially like a Python operating system. So you've got all these features that you're used to.
So when you were designing the hardware, what were some of the requirements that you were targeting in terms of performance or peripherals?
Well, the reason I chose the chip that I did was it was sort of the best chip I could find with the most RAM at the time, and that it wasn't expensive. It was relatively cheap, because that's what I wanted. I wanted something that was only a few dollars. It was about $10 if you buy them one-off chips that you could solder by hand. It's only got 64 pins, which is relatively small. It's relatively easy to solder by hand compared to some other things. So I wanted something that you could just get, and you could just solder it, and then hey, it runs MicroPython. And because I was designing the hardware at the same time that I was writing the software, I didn't actually know at the beginning how many resources I would need. So I picked the chip with the most RAM and the most flash, so that it would at least have some chance of running. And then if down the line it turned out I needed less, I could just shrink the chip and get a smaller one. But in the end, I kept this chip because it's actually very powerful, and it's got lots of cool peripherals like digital to analog converters and lots of DMA to do fast memory transfers, and it's a pretty capable chip. So, but yeah, it was chosen so that I could be sort of guaranteed that it would at least work. And now that MicroPython is quite mature, you can go and choose a sort of a less powerful chip to run it on if you so desire, that has the features that you need and costs you what your budget is. So you can buy like a $2 chip and run it on it now, and that's cool if you want to make thousands of it.
So what level of hardware knowledge is required to start working with the PyBoard?
Pretty much none. If you buy one, you just have to plug it into your USB port on your PC, and then you can sort of log into the board using a terminal program. Like if you're in Linux, you can just use Screen, or on Mac you can also use Screen. And on Windows, you can use Patti or Terraterm or something like that, just to connect to the COM port. And then you've got a Python prompt there straight away, and you can type LED on or LED off, and turn the LED on and off. And you don't need to know anything more than that. But if you want to, there's lots of features to explore. You can change the frequency of the CPU using pyb.freq, and then you type the frequency in and it changes the frequency. You can do low-level stuff like enable and disable interrupts with the Python call. You can create timer objects with one line and set their frequency, and then get them to do something every time they fire. So to begin with, you need almost no knowledge, and there's sort of a nice shallow learning curve to introducing all the peripherals and seeing what they can do and how you can use them. So you can do quite a bit just by plugging it into USB. It has an accelerometer, so you can read the angle of the board by a couple of lines. And so really it's just Python and then learning a few modules, the PyB module and the classes it has. So it's kind of no hardware at all in that respect. But then if you want to start connecting things up, like maybe some lights or buttons or motors or displays or Wi-Fi modules or things like that. Then you need to know a little bit about electronics, about how to connect things to the power supply and resistance and things. But I'd say it's probably a good way to get an introduction to these things if that's what you're interested in doing.
Definitely. And so it sounded like you were saying that there's a module namespace for interfacing with some of the hardware of the board. Is that correct?
Yeah, so there's a PYB module, which is stands for PyBoard. And if you import that, then under that module it has the classes for all of the peripherals. So each peripheral is a class, so the UART class controls the UART, which is a serial communications protocol. And so you can just create instances of these objects, and they correspond to a physical piece of the hardware, and then you just, like the UART has read and write methods to send and receive data, so you just read and write a text string. And then if you've got the UART connected to, say, another PyBoard, then you can communicate between the two just by doing UART.read and UART.write.
So how portable is that module? Is it able to run on other hardware devices, or is there some sort of an abstract base class that people can inherit from for implementing their own particular specific implementations for a given board?
We're trying to make it so that it's the code that you write for one PyBoard would run on another variant. I mean, if you write code for your PyBoard, it'll run on your friend's PyBoard because they're the same thing. But, for example, the Wi-Fi is a different board, but we've tried to make it so that they have the same classes. They have UARTs and they're used in the same way. They have LEDs, they're used in the same way with the same methods. So it's like if you write some code for one board, it should run on the other board if it has the peripherals are there. I mean, some boards won't have all the peripherals that you had on another one, but if they do, the code should run the same. So if you're trying to implement, or if you're trying to port MicroPython to a new board, then the idea is that you would take a look at how all the methods that UART has, and you'd make sure your UART object has the same methods and corresponds to the same behavior. And we've tried to make it so that that's possible to do, so it's, there's not some obscure behaviors. They're all very clear and it's clean. So as much as possible we try to do that so that it's easy to use. And just as another example, the way the Wi-Fi works, so on the Wi-Fi board, if you want to use the internet features, which of course you do, you can just use normal Python sockets. So there's no fancy things to do at all. You just import a socket module and you create a socket and you connect or you bind, and then you can make a server or a client. And it's as simple as that. So in fact, the script that you write for your PC to make a server or a client will be the same script that runs on the Wi-Fi. So it's sort of a seamless transition for your knowledge and also for testing purposes.
So for anyone who's interested in writing libraries, what kind of restrictions do they need to be aware of as compared with regular CPython?
Well, they need to be able to fit. They need to, if they're too big, then they just won't be able to be compiled into RAM. So, and that's just a sort of an almost hard limit because, you can't do everything. It's not going to fit, it's not going to fit. But given that it would fit, then really there's not much in the way of restrictions. All the Python language features are there. The inbuilt types like strings and dictionaries should all work just as you expect and have all their methods, or at least most of them. If your library relies on other libraries, then you'll have to make sure those other libraries can work. But otherwise, there's not really much in the way of restrictions.
And so do the C-based modules run on it as well, unaltered, or would the C implementations need to be rewritten?
The C stuff's different because that relies on a CPython specific API. So, for example, NumPy. That's written with special calls to CPython, which don't exist in MicroPython because MicroPython's internals are different. Now, we could write a sort of glue layer so that C code written for CPython could run on MicroPython. And I've looked at that and tried to do it, and yeah, it's possible to do, but not really an active area of work at the moment.
So what license is used for the MicroPython interpreter and the PyBoard, and are they compatible with commercial use cases?
So I mentioned before that MicroPython is MIT licensed, so that means that it's free completely for commercial use, for hobby use. You can take the source code, do what you like, change it, release something with it and not release the source code, that's up to you. So yeah, there's no strings attached. It's compatible with commercial use and compatible with hobby use or whatever you like. And the PyBoard itself, yeah, I mean, the schematics are there and you're free to make your own version. Some people have made their own. It's a pretty basic circuit, actually. It's supposed to be simple so that you can understand it as well. And if the PyBoard isn't exactly what you need, you can go and implement your own and run MicroPython on it. So the aim is to make it as accessible as possible and not to trap people in one particular piece of hardware or anything. That they're free to go and change the source code. You can write your own sort of extensions in C to the source, make your own board with your own chip, and yeah, do what you like. So I think it's good, and I think that helps the community grow.
So what are some of the most interesting and innovative projects that you've seen people make with the MicroPython board or runtime?
Well, I tried to make a quadcopter. These drones nowadays, they're very cool. And I have this quadcopter that's controlled with MicroPython, so it controls the servo, the motors, the propellers. It's not completely finished yet, but yeah, it does like a little bit. It can take off, but then you can't control it so well. So hopefully I'll get to finish that one day. But some other things people have been working on. So someone has made has controlled the guitar, so made a MicroPython controlled guitar, so that they actually pluck the strings and change work on the fret and can play chords. And so they have a PyBoard connected to all of these actuators so it can actually play the guitar. That's pretty cool.
So how does the experience of using MicroPython and the PyBoard and the YPy module compare to some of the other hardware projects that are popular right now, such as Arduino, Raspberry Pi, or the Tessel?
Well, the Arduino has been around for quite a while, and you're right, essentially writing in C++ when you're using an Arduino, and you need to compile and then download. Raspberry Pi, on the other hand, is a full computer, as you might know, and so you can write in whatever language you like and run on there. And MicroPython is sort of in between those two, the PyBoard is in between those two. It's more powerful than an Arduino, and I think more fun and more easy to use, because you get a prompt and you can turn on an LED with one line, whereas on an Arduino you have to compile your code and you've got all this boilerplate stuff and you've got to download it and then it will run, and if you get it wrong you've got to recompile and download it. But MicroPython you can sort of develop on the prompt to check things out and then write your script as you work things out. The Raspberry Pi, on the other hand, is like a full PC. It uses a lot of power, it's relatively big, it's relatively expensive in terms of the chip, and yeah, so it's in a different league again. So if you want something that's small and low power, as in doesn't use up much battery, then MicroPython is a good choice, and it's easy to program. The Tessel is sort of similar to MicroPython, but it runs JavaScript. So if you like JavaScript, then go for that. But I think Python's a much more friendly language than JavaScript to program in.
So is there anything that you wanted to talk about that we didn't ask you about, or anything that we should have asked you about?
So I don't know if you've heard the announcement that was made, but the European Space Agency is actually interested in MicroPython. So the European Space Agency is Europe's version of NASA, and they approached us and were asking whether we thought MicroPython could perhaps run in a space-based application, say up in orbit. And we said, yeah, maybe it could, and they have prepared to fund the development of MicroPython for the short-term future, to see if MicroPython is capable of controlling things in space, of doing things in constrained environments and in embedded environments that are very critical and have very critical limitations of them. So, if something goes wrong, that's a big problem. So you've got to make sure that the code is very well written and doesn't have any bugs in it, and that it runs as you expect it to. So that's very exciting, I think. So there'll be lots of interesting developments, I think, in the future, seeing if we can make MicroPython suitable for these really critical embedded systems.
So that brings up an interesting question as well as to whether or not MicroPython is capable of being used for any sort of real-time systems, whether hard real-time or soft real-time.
Yeah, so that's exactly the point with the ESA stuff, is that it's seeing if MicroPython can be used in systems such as real-time systems where things have to be executed by a deadline. You can't run out of memory. Things are critical. So, yeah, it's at the moment I wouldn't say use MicroPython for a critical system because it's not yet completely verified. There's still things that have to be ironed out. But I think in the future, if enough work goes into the runtime to make it suitable for real-time systems, then yeah, I think it's possible. But yeah, we'll have to wait and see because it's a little bit of uncharted territory. Normally you see for real-time systems, and you don't allocate any memory at all. It's just very basic stuff. So going all the way to Python is sort of a really big leap where you're allocating stuff on the heap all the time. You've got all these dynamic data structures, and you're doing lots and lots of different things, which are not, perhaps deterministic. So it's a big step, so it requires a bit of work to make sure that it's actually possible to do, to see if it's possible and what changes have to be made. Maybe you have to program in sort of a restricted Python, so you can't use, say, dictionaries because they allocate memory, or you can, but in a restricted way. So yeah, it will be interesting to see how far this can go and then whether or not it can be used in real-time systems.
That's really interesting, too, because it just struck me. I was at the Red Hat Summit this last week, and a few of the talks that I was at were talking about network function virtualization and how so much of the currently specialized hardware that runs networking devices for telecom and also for our, for the technology industry are these specialized devices with hard-coded firmware to do these tasks. And it's being moved into more general-purpose computers now, running specialized software to do the job. It strikes me that something like MicroPython might be a really interesting sort of middle ground, as opposed to having general-purpose computers with fragile disks running this stuff. It might be kind of interesting and neat to have MicroPython chips with Python-coded firmware doing some of these tasks.
MicroPython is, as we were talking about before, is sort of like when you're running it on bare metal, it's like the operating system itself. And yeah, there's no moving parts, it's running from Flash. It's only got a little bit of RAM, but it's got complete control over it. And because it's a managed system, then, you don't really have straight pointers. So it is a very interesting territory of, control systems. Yeah, is it possible to use such high-level languages for low-level control? So yeah, it's interesting.
At this point in time in the show, we'd like to transition into the picks. You can recommend anything that you might like or enjoy and think our listeners might like. So Tobias, why don't you kick us off?
So my first pick today is going to be the movie Machine Gun Preacher with Gerard Butler. It is the real-life story of Sam Childers' work in South Sudan to try and free the child soldiers that are embroiled in the conflict there. And it's a very well-done movie. It doesn't try to gloss over anything. It also doesn't try to glorify anything. And it's definitely worth a watch. My next pick is the Pocketbook Android app. It's the e-reader that I've been using on my tablet for a while now to read PDFs and EPUBs, and it's just got a really good design and good UX with a solid feature set that doesn't get in your way, so I've been enjoying that. And my last pick is a combination pick of Hoopla Digital and Overdrive, which are online platforms that let you access digital media, whether it's ebooks, music, videos, through your local library memberships. So if you have a library and you have a membership there, it's definitely worth checking out to see what sorts of other content you can get access to through those platforms. Chris, go ahead.
My first pick is Real Ramen. A lot of people, at least Americans, when you mention the word ramen to them, they think of what's known as pot ramen, those plastic ensheathed packets of generic noodles in a dubious flavor packet full of stuff. But the actual dish of ramen noodles is something completely and utterly different. And if you're lucky enough, as I am living here in Somerville, Massachusetts, to have a really great ramen place, right down the road from me. You should go there and you should get it and sit there at the bar and watch the ramen chefs prepare it, because it is a beautiful thing to watch. It is an art, and it is like nothing you've ever tasted. It's really pretty amazing. So that's my first pick. My second pick is the Red Hat Summit, which, as I said, I just went to last week. I walked in kind of not knowing what to expect, looking at the talk descriptions, thinking, okay, this looks like a lot of middleware, Java stuff, and I don't really know how much of it's going to be interesting to me. And oh my goodness, I walked away learning so much about Linux and where the internals are going, and performance tuning, and non-unified memory architectures, and SE Linux, and security, and containers. And it was just a great conference. I met a lot of great people, and it really surprised me. So if you're a Linux geek and you have any truck at all with the Red Hat CentOS world, I highly recommend it. And my last pick is something that I learned about and received through one of the talks that I attended there, called the SE Linux Coloring Book. Dan Walsh of Red Hat has become Mr. SE Linux in a way. And one of the ways, and he's very, very creative and really great speaker, and I highly recommend, if you ever get a chance to see him speak, you doing that. But he produced this coloring book which explains the basic concepts of how SE Linux works, in an attempt to get everyone to take the time to understand it and not just turn it off because you received an error message and said, and walked away. So it's very cool stuff. He also gave a really great talk that when it comes available, I'll pick it and link it here on container security last week. That was really great. And that's it for me. Damien, what picks do you have for us?
Well, I'm going to be technical and say, I don't know if you've heard of this program, but Mosh, the mobile shell, I don't know, maybe you already use it, but it's been around a couple of years, but I think it's a really fantastic piece of software. It basically replaces SSH and allows you to, it is SSH, but Mosh stands for Mobile Shell, and you can Mosh into your machine just like you would SSH in, but then if your Wi-Fi or internet connection goes down, you don't lose the session. It comes back when your Wi-Fi comes back, so you can actually put your laptop to sleep with a Mosh session open, and then when you wake your laptop up again, the Mosh session will reconnect, and you just have everything there like you did before. So that's something that I use all the time, and I think it's really useful. Especially when if you're sick of SSH and drop connection, then definitely need to use Mosh.
That's great. I have used the Mosh shell, and it does make it very useful for when you're dealing with different servers on a regular basis, because having SSH connections drop can be very annoying and potentially problematic if you forget to run your command and screen or tmux, and then all of a sudden your connection drops and your 2-hour-long compilation session fails because of that.
Yeah. I use it all the time.
So, Damien, we'd like to thank you very much for taking the time out of your day to join us and talk to us about the MicroPython project. It's been very fascinating, and I'm sure our listeners will really love to hear about it. So, for anybody who wants to keep in touch with you and follow what you've been up to, what's the best way to do that?
So just go on GitHub. I think that's the best way. Go to github.com/MicroPython, and that's where the MicroPython code lives. And you can star the repository, and you can watch the repository, and then you'll get all of our conversations, all of the development work. It'll be a stream that you, it will annoy your inbox, but a stream of consciousness of the development of MicroPython. And you can raise issues there, and you can sort of contact us that way. Yeah, I think that's the best way to stay in touch. Thank you for having me. It's been a pleasure.